Dear students, in this video we will talk about pericyclic reactions. The term pericyclic comes from peri and cyclic. Peri means around and cyclic stands for cycle. So it means pericyclic would mean around the cycle. We can define pericyclic reactions are those reactions which proceed in a single concerted step via a cyclic transition state involving sigma and pi electrons. So definition of pericyclic reaction would be reactions which proceed in a single concerted step via a cyclic transition state involving sigma or pi electrons would be pericyclic reactions. Now there are four types of pericyclic reactions. Electrocyclic reaction, then cycloaddition reactions, sigmatropic rearrangements, and group transfer reactions. So these are four types of pericyclic reactions. Now we explain electrocyclic reactions. In electrocyclic reactions, compounds with conjugated double bonds form a cyclic molecule. And in these cases, 2 pi electrons are used to make a sigma bond. And in these cases, either a ring is formed with new sigma bond and loss of 2 pi electrons and vice versa. For example, we have 1, 2, 3, 4, 5, 6, 1, 3, 5 hexatriene. It undergoes electrocyclic reaction, and as a result of it, we get 1, 2, 3, 4, 5, 6, 1, 3 cyclohexadiene. So this is the example of electrocyclic ring closing reaction. Electrocyclic ring closing reaction, and in this case we can see here we have a new single bond, sigma bond is being formed here, and we had 3 pi bonds here, and now we have 2 pi bonds here. So 2 pi electrons have been used to form this. So this states that either a ring is formed with new sigma bond here and loss of 2 pi electrons. So 2 pi electrons have been used to make this sigma bond. For example, we can take these 2 pi electrons to make this sigma bond, and it can be vice versa. And how it is vice versa? For example, in an electrocyclic ring opening reaction, for example, this shifts here, this shifts here, we get 1, 2, 3, 4, 1, 3 butadiene. And in this case, a sigma bond is converting into 2 pi electrons here, and so this is basically the explanation of vice versa. So it can occur through 2 ways, either electrocyclic ring closing reaction, this one, and it involves a ring formation with new sigma bond and loss of 2 pi electrons. And in case of electrocyclic ring opening, we have a sigma bond broken and we get 2 pi bonds. So this is electrocyclic reactions. Now we see other types. First type was electrocyclic reactions, which we have just studied. Second is cycloaddition reactions. In cycloaddition reactions, we again have a cyclic transition state, and 2 molecules add together, and they make a cyclic molecule, and it involves again cyclic transition state. And for example, we have the example of 4+2 cycloaddition, which is the Diels-Alder reaction, and we get this one. So this is cycloaddition reactions. And third one is sigma-tropic rearrangements. So next is sigma-tropic rearrangements. In sigma-tropic rearrangements, one molecule, one atom or group of atoms is shifted intramolecularly from one position to another. For example, we have this molecule, and as a result of sigma-tropic rearrangement, we will get this. So this is sigma-tropic rearrangement, and we will study the details of all the reactions later again. I hope these all definitions or basic concepts are clear to you. Okay, now we see the features of pericyclic reactions. First feature would be they are single step reactions. So the reaction takes place in a single step, and in general solvent has no effect. And solvent has no effect because they do not involve the formation of ionic or radical intermediates. And next feature is they are initiated thermally or photochemically. This means that for the initiation of the reaction we need heat or light to start the reaction, and these reactions are highly stereospecific in nature. For example, if we have this molecule under heating conditions, we would get the anti-isomer of the product. And if we perform the same reaction under light, we get syn product. These two groups are opposite, therefore it is anti, and here we have syn. And this is trans 1 2 3 4 5 6 2 4 hexadiene. So these reactions are highly stereospecific, and thermal or photochemical conditions can influence the formation of different isomers. However, still they are stereospecific. So I hope this is all clear to you. Now we see the theoretical basis of pericyclic reactions. Okay, now we see theoretical basis of pericyclic reactions. In 1965, Woodward and Hoffman proposed principle of conservation of orbital symmetry. According to this theory, the symmetry of orbitals of reactants and products should correlate. So according to this theory, there are two types of reactions: symmetry allowed and symmetry forbidden. If the symmetry of orbitals in the reactants, symmetry of orbitals in reactants are same as those of the products, the reaction would be symmetry allowed. And if symmetry of orbitals in reactants are different than those in products, so the reaction would be symmetry forbidden. So this was the theory proposed by Woodward and Hoffman, and another theory was proposed by Kenichi Fukai. And according to this theory, we have two types of frontier orbitals, molecular orbitals. And these are HOMO and LUMO. This is highest occupied molecular orbital, and LUMO is lowest unoccupied molecular orbital. So these are some theoretical bases of different theories. In general, this approach is simpler than this one. Okay, now we see molecular orbital theory. As per this theory, molecular orbitals are formed by linear combination of atomic orbitals. Linear combination of atomic orbitals. And if we see the example of saturated hydrocarbons, for example alkanes, we have two types of bonds, carbon-carbon bonds and carbon-hydrogen bonds. And in alkanes, all carbons are sp3 hybridized. So carbon-carbon bonds are formed by the overlap of sp3 orbitals overlap, and carbon-hydrogen bonds are formed by the overlap of sp3 and s orbitals overlap. So these are two types of bonds present in alkanes. There are two ways when two orbitals can interact. When orbitals interact with same phase, we get bonding orbitals, and when orbitals of different phase interact, we get anti-bonding or anti-bonding molecular orbitals, and they can be differentiated by shading. For example, orbital can be differentiated by shading or with a positive or with negative sign. So we can show the orbitals and phase of the orbitals via shading or unshading or positive or negative sign. So I hope this is all clear to you. Now we see some further details. Okay, now we see conjugated pi molecular orbitals. We know that there are two types of bonds, pi bonds or sigma bonds, and sigma bonds are formed by head-to-head overlap of orbitals, whereas pi bonds are formed by side-to-side overlap of orbitals. So here we are concerned about pi molecular orbitals. Pi molecular orbitals are formed by side to side overlap of p atomic orbitals, and pi is a Greek letter for p. So these p atomic orbitals can be 2, 3 or more, and when we have 3 or more side to side overlapping p orbitals, this is called conjugation. In general, we know that the alternating double bond and single bond, this is conjugation, and of course this is also conjugation, but this is one type of conjugation. The comprehensive definition would be 3 or more side to side overlapping p orbitals. So now we see some examples of molecules having p orbitals. First molecule is ethylene, which is CH2 double bond CH2. In this case, both of the carbons are sp2, and sp2 carbons have also a p orbital. So we have p orbital for this and p orbital for this with 1 electron each, because we have 2 electrons here. So according to the law of conservation of orbitals, the number of atomic orbitals will generate same number of molecular orbitals. So we have 2 atomic orbitals here, so we would have 2 molecular orbitals, and it would be, this is molecular orbital and these are atomic orbitals, and this is pi, this is pi star. If we place a central line, the orbitals below the central line would be bonding orbitals, and above the central line would be anti-bonding orbitals. So this would be anti-bonding, and this is bonding, and those orbitals which would fall on the central line would be called non-bonding. So this would be shown by shading, and in bonding interaction we have same phase of orbitals, so both would be represented as shading and would show maximum bonding interaction. And at this stage we don't have any node. Here we would have a node because here opposite phases are present. So this is above side, so other one would be downside, and that is why it is called anti-bonding orbitals. And now we see electron diagram. We have 2 electrons, so according to Hund's rule, these 2 electrons would have opposite spin and would stay here. So this is HOMO, highest occupied molecular orbital, and this would be LUMO, lowest unoccupied molecular orbital. So this is the molecular orbital diagram for ethylene. Now we see another example. Next example is this molecule, propionyl cation. This is sp2 hybridized, this is sp2 hybridized, and carbocations are also sp2 hybridized. So each sp2 carbon has p orbital as well, so we have 3 p orbitals, and these 2 can have electrons because we have shown pi electrons here, pi bond, and here we don't have electron, but the orbital is there. This is just like that, we have a pocket, but even without money it still exists. These are 3 atomic orbitals and they would give rise to 3 molecular orbitals, and each should have 3 orbitals, atomic orbitals in it. This is on the central line, so these are non-bonding, and this is pi, this is pi star. So we show maximum bonding interaction here, so all would be having same shading. And here, because we have the problem of symmetry, if we shade these two, this has to be down. So it is better to omit this orbital. So in this case, central orbital would be omitted. However, we will keep the space to show the existence of an orbital. So here we have one node, and because as we go higher towards higher levels, nodes are increased, and here we have one, and here we have second node. So 0 node here, 1 node, 2 nodes. And electron diagram, we have 2 electrons, so all would come here. And this is HOMO, and this would be LUMO. So I hope this is clear to you. And next example could be propionyl anion. Again, this is sp2 hybridized, this is sp2 hybridized, and this is sp2 hybridized. In general, carbanions are sp3 hybridized. Carbanions are sp3 hybridized. And when they are connected to sp2 carbon, they are also sp2 hybridized. So in general, carbanions are sp3 hybridized, but when they are connected to sp2 carbon, they are sp2 hybridized. So we have again 3 p orbitals, electrons, and again 3 molecular orbitals. Here again we will omit the central orbital due to the symmetry issue, because we cannot create symmetry in the middle, therefore it would be eliminated, and we will have a node here, but we will leave the space for an orbital. Here 2 nodes, and here 0 node. Again pi, these are non-bonding, anti-bonding. And electron diagram, so we have 2 electrons here and 2 here. So this is now HOMO, and this is LUMO. So I hope this is clear to you. And another example would be propionyl radical. Again, we have all 3 sp2 hybridized, because radicals are also sp2 hybridized. So we have 3 orbitals, and now we have 3 molecular orbitals again. In the central we have again 2 to maintain the symmetry. Two nodes, and here we have 2 electrons, one from the radical. So this is HOMO now, highest occupied molecular orbital. This would be LUMO. So I hope this is all clear to you. Now we see the molecular orbitals of 1,3-butadiene. So next example is 1,3-butadiene, and again all are sp2. There are 4 carbons sp2, so 4 p orbitals we would have here, and as a result 4 molecular orbitals, and each has 4 atomic orbitals. So first is pi1, pi2, here is the middle, so it would be pi3 antibonding, pi4 antibonding. So pi1 is bonding, and here we would show maximum bonding interaction, so all would be shaded. And here we will have 1 node. And in the next level, pi3 antibonding, we would have 2 nodes. And in pi4, you would have pi4 star, we would have 3 nodes. And we see first and last orbital has same symmetry, and it is also symmetric in the center, so this is represented as S. Then first and last has opposite symmetry, and also it has a node in the center and opposite symmetry in the center, so this is antisymmetric. So it would be symmetric, antisymmetric, symmetric, antisymmetric. So first and last has the same, and we have the same symmetry in the middle. So antisymmetric, first and last has different, and also opposite symmetry in the middle. So next we see the electron diagram. So we have 4 electrons, 4 pi electrons. So 1 pair would come here, second pair would come here. So this is HOMO, and this would be LUMO. So I hope this is all clear to you. If you find any question or confusion, please leave your questions in comment box. Thanks.